So this video is going to cover chapter 16, aromatic compounds. So just a cool and fun history of the discovery of benzene. In 1825, there was a scientist by the name of Michael Faraday, and he was able to isolate a really pure compound, and he noticed that it had a small hydrogen to carbon ratio of 1:1 after doing a whole bunch of analyses. And then in 1834, Eilhard Mitscherlich, who was a German chemist, synthesized the exact same compound that Michael Faraday was able to isolate. And he also noticed, wow, this has a really small hydrogen to carbon ratio of 1:1. And he determined that it actually has a molecular formula of C6H6. So he actually synthesized this compound from gum benzoin, which is a type of sap that's found in specific trees. And so because of that, he named this structure benzene, which is what we now know as benzene. So in the 19th century, there were many compounds that were similar to benzene that had low hydrogen to carbon ratios. And what all of these discoveries, what was a common denominator was they all had a pleasant aroma. Like all these structures with low carbon to hydrogen ratios smelled really good. And because of that, we call these structures aromatic compounds. However, the road to determining what exactly is aromatic or non-aromatic or anti-aromatic wasn't always easy. So that's what we're going to cover in chapter 16. So benzene has a carbon to hydrogen ratio of 1:1, a very, very low ratio. Benzene is also a resonance hybrid between two kekulate structures. So the kekulate structure proposed that benzene structure had longer carbon-carbon single bonds and short carbon-carbon double bonds. And that is a fair hypothesis that is totally plausible because generally, like how we've learned, carbon-carbon single bonds are longer than our carbon-carbon double bonds. However, that is actually not true. In benzene, all of the carbon-carbon bonds are of all the same length. And so the kekulate structure, we draw it like this, where we have all of our single and double bonds alternating. However, doing a combined representation over here is more of a proper way to, I guess you could say, to draw our benzene. Some more properties and the structure and characteristics of benzene. It is a planar molecule. It is a six-membered ring. It has a conjugated system. All of the bond angles are 120 degrees, and the bond lengths are of all same length of 1.397 angstroms. Also, each carbon is sp2 hybridized, and this is very important. All of the unhybridized p orbitals are going to contain our pi electrons, and they're going to all overlap with each other. And they are going to participate in this ring energy. And so we know that each pi bond holds two pi electrons. So benzene has 6 pi electrons, 2, 4, 6. And so anyways, looking at all of these, the properties and the structure of benzene, scientists determined, okay, benzene is an aromatic compound. And they were totally right. Benzene even has a very stable resonance energy. So whenever we get our resonance structure, we have a resonance energy of 1.51 kilojoules. And it had a predicted energy of actually 359 kilojoules per mole. And so resonance energy is just the difference between your predicted energy and the actual energy. So they saw that whenever we got the resonance structure, that it's very, very, very stable. As a matter of fact, in chapter 8, we learned about how reactive our carbon-carbon double bonds are, right? So, for example, if we were to react this with some cold and dilute potassium permanganate, we'd expect to see a syn dihydroxylation reaction occur. However, benzene is so stable, these double bonds are so stable that if we try to react this with cold and dilute potassium permanganate, no reaction is going to occur. So that just goes to show how stable aromatic compounds are. So, chemists saw the characteristics that benzene exhibited. And so they noticed, whoa, this has a conjugated system, it has a low carbon to hydrogen ratio, and we can get pretty much almost an identical resonance structure. So that must mean that all compounds with a conjugated system and are cyclic must have an identical resonance structure that is going to be extremely stable. However, that wasn't correct, but it was a good hypothesis. If we look at cyclobutadiene, here we can see we definitely have a cyclic structure, we have a low carbon to hydrogen ratio, and we have a conjugated system. So they assumed, man, this must be aromatic. But if you get the resonance structure of our cyclobutadiene, we actually can't do that. This is not possible. Cyclobutadiene cannot be isolated because it is extremely reactive. And we know that benzene is super, super stable. It doesn't react with potassium permanganate, or if we were to do a bromine test of unsaturation, there is no reaction. Whereas cyclobutadiene over here is super, super reactive. So that can't be an aromatic compound. And then cyclooctatetraene, here we see that we have a cyclic structure. We have conjugated systems right here. We have, so if we were to get the resonance structure, if we were to test their hypotheses, oh, I don't know how to draw this sucker. Two things about cyclooctatetraene: it is still less stable than benzene. It is still a reactive compound, but also cyclooctatetraene is non-planar, whereas benzene is planar. So this hypothesis that you just have to be a cyclic structure with a conjugated system, and you have an identical resonance structure that will lower your electronic energy, it was incorrect. However, we don't call all of these aromatic compounds. Instead, we say that these are annulenes. Annulenes are just hydrocarbons with alternating single and double bonds. And so if we were to even take a look here at our 10-annuline, our cyclodecapentene, here we have two trans hydrogens, or we have two trans double bonds. Therefore, our hydrogens are going to interfere with each other. Therefore, we do not have a planar structure. So this right here cannot be an aromatic compound. So this leads us into the next part of our video. How do we determine what will be aromatic or anti-aromatic or non-aromatic? Because we learned that going simply with the definition of having to be a cyclic structure with a conjugated system and an identical resonance structure, that wasn't correct. So to be aromatic, you do have to be a cyclic structure, and it must contain conjugated pi bonds. Each atom within the ring must have an unhybridized p orbital. So we got to be sp2 or we got to be sp. But what we'll be looking at in this chapter is mainly sp2 hybridized atoms. To be aromatic, the structure must also be planar. And anytime you have an sp3 hybridized carbon, in your structure, automatically that is non-planar. So these 2 points kind of coincide with each other. Also, whenever we delocalize our pi electrons in that ring energy, it must lower the electronic energy. It must be stabilized. And also, it must follow the 4n plus 2 Huckel rule. N is going to be any integer. You can start with 1, 2, 3, 4, 0. It doesn't matter. And anyways, our 4n plus 2 must add up to 6 pi electrons, 10 pi electrons. This is to help us count how many pi electrons we have. So for example, if we take a look at benzene, we see that this is a cyclic structure. We have our conjugated system because we have all of our double bonds separated by a single bond. All of these carbons are sp2 hybridized. So because of that, we know that this is a planar structure. We saw that whenever we draw the resonance structure, that it does lower the electronic energy. And if we count our pi electrons, we have 2 in this double bond, 2 over here, 2 over here. So we have 2, 4, 6 pi electrons. Using the 4n plus 2 rule, again, n is any integer. I'm going to start off with 1. 4n, which will be 1 in this example, plus 2, is going to give me 6. This follows the 4n plus 2, so I know that this is going to be an aromatic compound. Anti-aromatic compounds, for the most part, are going to follow a lot of the same characteristics as aromatic compounds. They're still going to be cyclic structures and they'll have conjugated pi bonds. Each atom within the ring will also have unhybridized p orbitals that are going to overlap with each other. They're also going to be planar. However, the delocalization of our pi electrons, instead of lowering the electronic energy, it's going to increase the electronic energy. Also, instead of following 4n plus 2, it's going to follow the 4n rule. So if we look at cyclobutadiene, cyclobutadiene is a cyclic structure. We see that it has a conjugated system. All of our carbons are sp2 hybridized, so it is a planar molecule. However, we just went over in our anilines how we're not able to get our resonance structure. It can't be isolated because it's extremely reactive. However, if we go ahead and count our pi electrons, we have 2 in this double bond, 2 in this double bond, 2 plus 2 is 4. We have 4 pi electrons, and if we use our 4n Huckel rule, n is any integer. I'm just going to start with 1. 4 times 1 is 4. And so, because this follows the 4n rule, this is said to be anti-aromatic. Now, non-aromatic compounds, they're, instead of going to be cyclic, they'll be acyclic instead. They can lack a conjugated system, or they're going to be non-planar. They don't necessarily require all 3 of these. They don't require necessarily all 3 of these components to be non-aromatic if they lack just one of these components. So, for example, if we look at cyclohexene, this is a cyclic structure. However, because it lacks a conjugated system, automatically this is going to be non-aromatic. Or if we look at penta-1,3-diene, this does have a conjugated system, but because this is acyclic, this is not a cyclic structure, automatically this is going to be non-aromatic. So if we're lacking just one requirement, we're going to be non-aromatic. So if we look at cyclooctatetraene or 8-aniline, This is a cyclic structure. This also contains a conjugated system. However, this is a non-planar structure, even though all of our carbons are sp2 hybridized. So once we start getting at larger cyclic structures that contain 8 carbons and more, it'll be a little bit more difficult to determine, is this going to be planar or will it be non-planar? So whenever you take your exam, in the questions, if you're asked to determine whether a structure is aromatic, antiaromatic, or non-aromatic, and if it's a larger molecule, then it will be specified if the molecule is planar or non-planar. But anyways, cyclooctatetraene has what we call a tub conformation, which pretty much just shows that it is not planar. And because it's not planar, all of our unhybridized p orbitals are not able to overlap the way that they're supposed to. Let's look at cyclopentadiene. Cyclopentadiene is a cyclic structure. It contains a conjugated system. However, this top carbon right here is sp3 hybridized. And because this is sp3 hybridized, this is a non-planar structure, making this non-aromatic. If we look at some 10-aniline examples right here, this structure right here would be non-aromatic because there is so much ring strain within all of these cis double bonds. Whereas this structure over here, because of the 2 trans double bonds, our hydrogens are going to interfere with each other. It's a non-planar structure. This is non-aromatic. However, if we look at naphthalene, this is what we call a polynuclear aromatic hydrocarbon, and we'll cover this in just a little bit, but essentially, these are many aromatic compounds that are fused together. And these are planar. So if we gone ahead and count all of our pi electrons, we have 2, 4, 6, 8, 10. We have 10 pi electrons. We see that this is cyclic. This is planar. We have a conjugated system. So using our 4n plus 2 rule, again, start with any, n can be any integer, start with 1. If we use 1, 4 times 1 is 6 plus 2. 4 times 1 is 4 plus 2 is 6. Let's go ahead and use 2 as our integer. 4 times 2 is 8. 8 plus 2 is 10. This follows the 4n plus 2 rule, and because of that, naphthalene is an aromatic compound. So moving into cyclopentadienyl and cycloheptatrienyl ions. So we just learned that cyclopentadiene is non-aromatic due to that sp3 hybridized carbon. However, if we were to get the cyclopentadienyl cation, this first structure over here, we now have an empty p orbital. And we know that carbocations are sp2 hybridized. So now we can say confidently that all of our carbons are sp2 hybridized. And if we count our pi electrons, we have 2, 4 pi electrons. And this is going to follow our 4n rule. 4 times 1 is 4. So because of that, this is said to be antiaromatic. Whereas if we were to look at the anion, even though this carbon right here, we know that carbon ions are sp3 hybridized. However, they can rehybridize to a p orbital, and that is what we're seeing right here. And they are actually going to participate in our ring. So, because of that, if we count our pi electrons, we have 2, 4, and then our lone pairs, which are going to be in a p orbital, 6 pi electrons over here. This is going to follow our 4n plus 1 or 4n plus 2 Huckel rule whenever n is acting as 1. So the cyclopentadienyl anion is actually going to be an aromatic compound. And so essentially that is what this picture is explaining right here. If we were to depronate our cyclopentadiene and get the cyclopentadienyl anion, we now have 6 pi electrons because we have 2 electrons in our p orbital, making it an aromatic compound. If we look at our cycloheptatrienyl ions, same thing over here. If we look at cycloheptatriene, we have sp2, sp2, sp2 all around here, but this top carbon right here is sp3 hybridized. And because this is sp3 hybridized, this is a non-planar structure. And so even though this is cyclic and it has a conjugated system, because we have a because we have an sp3 hybridized carbon, making it non-planar, this is going to be non-aromatic. However, if we were to perform this right here is a dehydration of an alcohol reaction. If we were to dehydrate our alcohol and remove it, leaving us with the carbocation right here, this carbon is now sp2 hybridized because we have an empty p orbital. And if we count our pi electrons, we have 2, 4, 6 pi electrons. That is going to follow our 4n plus 2 Huckel rule, making it aromatic. However, if we were to have an anion instead of a carbocation, if we were to count our pi electrons, making sure to count this lone pair right here because it will be in a p orbital, therefore it's contributing to the ring, we will now have 2, 4, 6, 8 pi electrons for our carbon ion. And 8 pi electrons is going to follow our 4n rule if we use 2 as our integer. 4 times 2 is 8. Therefore, the carbon ion would be, or the cycloheptatrienyl anion would be an antiaromatic. That structure tripped me up. But anyways, this is how just other ways that we can apply the rules determining whether we have a planar, a non-planar structure. If we have lone pairs, looking at how they are going to be participating in the ring because they're going to be in a p orbital. So we have just been focusing on hydrocarbons for aromatic compounds. Now we're going to move to heterocyclic aromatic compounds. So now we're going to start introducing nitrogens. We will also go over a few examples that have oxygen and maybe even sulfur. We say these are heterocyclic aromatic compounds because now we're containing more than just carbon and hydrogen. And here we can have what we call basic and non-basic nitrogens. Basic and non-basic nitrogens just depends on whether our lone pairs are participating in our ring or if they're not. We know that nitrogen is trivalent, so in a neutral state, it makes 3 bonds and has 1 lone pair. So if we take a look at pyridine, this nitrogen is making 1, 2, 3 bonds. So we know that in a neutral state, we're going to have 1 lone pair. And this lone pair is going to be in an sp2 orbital. So this is not going to be participating in our ring. So if we were to count our pi electrons, we'd only count 2, 4, 6. We would not count the lone pairs right here. So this has 6 pi electrons. This is definitely aromatic. And this nitrogen is said to be basic. This is a basic nitrogen because with this lone pair, we are capable of accepting a proton, which would then put our nitrogen in a positive state, but this nitrogen is basic. However, if we look at pyrrole, this nitrogen is also making 3 bonds, 1, 2, 3 with that hydrogen. However, our lone pairs are going to be participating in the ring. So whenever we count our pi electrons, we would have 2, 4, and 6 right here, because these lone pairs are actually going to be in an unhybridized p orbital. And so this nitrogen is actually sp2 hybridized. So it has 6 pi electrons. So this is also aromatic. However, because our lone pair is participating in the ring structure, this is said to be non-basic, because it's not really capable of accepting a proton if the lone pair is already participating in the ring. Another way to determine between basic and non-basic nitrogens is anytime we have carbon double bond nitrogen, that's going to be basic. So right here in pyrimidine, carbon double bond nitrogen, basic. Carbon double bond nitrogen, basic. We are not participating in the ring. If we look at our imidazole, carbon double bond nitrogen, basic. Here at this nitrogen, we are non-basic. We don't have that carbon double bond nitrogen. Our double bonds are actually going to, our lone pairs will be participating in our ring. And if we look at purine over here, now we have a larger fused heterocyclic compound. But this structure has 3 basic nitrogens. So make sure you're able to identify what is a basic and a non-basic nitrogen, knowing what to count as pi electrons, knowing what not to count as pi electrons. Our non-basic nitrogens have lone pairs that are participating in the ring, so we're going to count those as pi electrons because they're in p orbitals. However, our basic nitrogens have lone pairs in sp2 hybridized orbitals. They are not participating in the ring. Therefore, we do not count them whenever we're counting our pi electrons. But pyrimidine, here we have 2, 4, 6. 2, 4, 6. That lone pair is going to participate because it's non-basic. Then we have 2, 4, 6, 8, 10 pi electrons in our purine because we have that one non-basic electron or lone pair. That one non-basic nitrogen. So make sure you're able to identify all of your basic, your non-basic structures. Be able to put them in order from most basic to least basic, and even most acidic to least acidic. So I'm going to label this A, B, C, D, and E. Go on ahead and pause this video and put all of these structures in order from most basic to least basic. So here in pyridine, we see that we have 1 basic nitrogen. Here we have 0 basic nitrogens. In pyrimidine, we have 1 basic and 1 non-basic. In pyrimidine, we have 2 basic nitrogens. And our imidazole, we have 1 basic and 1 non basic. And then in our purine, we see that we have 3 basic nitrogens. So automatically purine, E is definitely going to be the most basic compound. Then it's going to be our pyrimidine. We know that because purine has no basic nitrogens, that it is going to be the most acidic or the least basic. Now, whenever we just compare our imidazole and our pyridine, pyridine will take priority because even though they both have 1 basic nitrogen, our imidazole is still going to be a little bit more, it's going to be less basic because we have 1 non-basic nitrogen over here. So that's how we could rank these in increasing, decreasing basicity, or even acidity if we were to get the conjugate acids of all of these structures. Moving into our polynuclear aromatic hydrocarbons, again, these are just going to be larger structures where we're going to have fused rings and we're going to share 2 carbons where we're going to fuse together. And so an example that we went over not too long ago was naphthalene, which is a 10-aniline. And all of these are going to be aromatic. We see that they all are cyclic structures. They all have conjugated systems. And because we're fused together and we share carbons where we're fused, this is also going to help us maintain a planar conformation. Now we're going to go into common names, how we name our benzene derivatives. Make sure, I forgot to mention this, but with our heterocyclic aromatic compounds, make sure you're familiar with all of their common names. Be familiar with them. Know how to name them. Oh, and I said I would go over an example where we don't have nitrogen, but we have another heterocyclic compound. So this right here is what we would call furan. Furan is going to be an aromatic compound. This is a cyclic structure. It's conjugated. Our oxygen now has 2 lone pairs though. So this lone pair right here is going to be in a p orbital that will be contributing to our ring, whereas this lone pair will be in a hybridized orbital that is not contributing to the ring. So if we were to count all of our pi electrons, we would have 2, 4, 6. We would have 6 pi electrons, which follows our 4n plus 2 rule. Make sure you do not count this other lone pair. This is not participating in the ring. This has only 6 pi electrons, not 8. But going back to the common names of benzene derivatives, I'm going to cover this, but this is really just something that you're going to need to memorize. You'll need to know. But whenever we have an alcohol as a substituent coming off of our benzene ring, this is an alcohol, so we call this phenol. Whenever we have just a methyl group coming off of benzene, this is toluene. Whenever we have an amine, NH2, coming off of our benzene, this is aniline. And then whenever we have an O-methoxy group as a substituent, this is anisole. So like the phenol and aniline, that kind of makes sense. Like aniline, amine, alcohol, phenol, that makes sense. However, toluene and anisole, just memorize those. Whenever we have a vinyl group as our substituent, this right here is what we call a vinyl group. This is styrene. Here, we could see that this is a ketone. This is one of our functional groups. And so this is acetophenone, ketone, acetophenone. That makes sense. Here we have an aldehyde, that hydrogen coming directly off of the carbonyl group. Benzaldehyde, that one's easy. Here, COOH, this is a carboxylic acid. So, whenever we have carboxylic acid acting as a substituent coming off of our benzene ring, this is benzoic acid. So really just make sure you know how to identify your functional groups, and the common names really make sense. But styrene, toluene, and anisole, those I feel are kind of ones that you just kind of have to memorize. Now we're going to go over disubstituted benzenes. So the placement of our substituents whenever we have two is actually really important, and we're going to see how they actually play a role in our physical properties of aromatic compounds. So anytime we have two substituents that are in the 1 and 2 position, this is said to be ortho. So this structure right here, this is O-dichlorobenzene. O because our chlorines are in the 1 and 2 position. Whenever we're in the 1,3 position, we are said to be meta. So this is M-chloroperoxybenzoic acid, or meta-chloroperoxybenzoic acid. Whenever we number, if we have a functional group, that will take priority over all of the other substituents. So this peroxy acid is going to be carbon 1, whereas our chlorine is going to be 3. Chlorine does not take priority over the peroxybenzoic acid. Which, by the way, MCPBA, metachloroperoxybenzoic acid, this is what we use for an epoxidation reaction, MCPBA. It's a peroxy acid. Anyway, so it's just cool to, tie concepts from previous chapters. And then whenever we have our substituents in the 1,4 position, they are para. Again, our alcohol will take priority over our nitro group. So alcohol will be 1, and our nitro group is going to be 4. So this is p-nitrophenol. We just got done talking about common derivatives. If we were to not have this benzene group over here, if we were to not have this nitro group right here, then this would just be a phenol. But this is a phenol group with a nitro group at the 4 position for nitrophenol, or PE, para-nitrophenol. Lastly, we're going to go over the physical properties of aromatic compounds. Aromatic compounds have higher melting points whenever compared to aliphatic compounds. Aliphatic compounds are really just acyclic structures. Also, the boiling point is going to be dependent on the dipole moment. So the larger the dipole moment, the larger the boiling point. And this is how using our 1,2, 1,3, or 1,4, our ortho, meta, and para is going to help us determine physical properties. If you had to rank, 3 structures in order of increasing boiling point. So in the first structure, I have my chlorines at the 1,2 position. So this is going to be ortho-dichlorobenzene. Here my chlorines are in the 1,3 position. So this is going to be meta-dichlorobenzene. And then in the last structure, my chlorines are in the 1,4 position. So this is going to be para-dichlorobenzene. So if we were to put these structures in order of increasing boiling point, so we want to start with our lowest boiling point and then work towards the highest boiling point. We know that the greater the dipole moment, then the larger the boiling point. Our para-dichlorobenzene is going to have the lowest boiling point because we've got that equal pull in opposite directions. So this is really almost going to zero out. So our para will have the lowest boiling point. And then whenever we compare our ortho versus our meta, because our chlorines are closer in our ortho, they're going to have a greater pull. Whereas because our chlorines in our meta are spaced out, they're separated by a carbon or 2 single bonds, the pull isn't going to be as great. So then it's going to be para, meta, and then ortho. And that is a common theme that you are going to see with aromatic compounds. Whenever, as far as talking about boiling point and it being dependent on the dipole moment. So the larger the dipole moment, the larger the boiling point. Our ortho has a greater dipole moment, and then meta, and then para has the smallest dipole moment. Also, aromatics are going to be more dense than non-aromatic compounds, but they are still going to be less dense than water. Lastly, aromatic compounds, they are non-polar compounds for the most part, especially whenever we're just looking at benzene, no derivatives. I mean, they're all carbons and hydrogens. And then on top of adding in those double bonds and whatnot, I mean, they're non-polar compounds. So aromatics generally are insoluble in water. But that is going to conclude Chapter 16, aromatic compounds. Really, what you really should be focusing on for this chapter is knowing how to determine whether a structure is aromatic, non-aromatic, or anti-aromatic. Know all of the rules and the requirements that will qualify a structure to be an aromatic or a non-aromatic or an anti-aromatic, looking out for whether it's planar, if it's cyclic, conjugated, if it follows the 4n+2 rule or the 4n rule. Knowing which, for heterocyclic compounds, if we're going to have a basic or a non-basic nitrogen, carbon double bond nitrogen is going to be basic. The lone pairs will not participate in the ring. If our nitrogen is just all single bonds and we're connected to another hydrogen, then our lone pair will participate in the ring in that p orbital. It's sp2 hybridized, and therefore it's going to be a non-basic nitrogen. Make sure you're familiar with the names for your heterocyclic compounds, knowing your purines, your pyrimidine, all of that stuff. And also knowing the common names of our benzene derivatives, our phenol, the benzaldehyde, the benzoic acid, all of that. And then going over our disubstituted benzenes, our ortho, our meta, our para positions. So yes, that concludes chapter 16. If you have any questions, please feel free to reach out to me.